Dear students, today we will see the gamma function. Gamma function is one of the technique to solve the real definite integral. Now here is the definition of the gamma function. Gamma function is denoted by the notation gamma n, and you can read as a gamma n. Suppose if we have the integral of the form 0 to infinity e raised to minus x raised to n minus 1 dx. It is this type of integral is denoted by the symbol gamma n, and we can read it as a gamma n, and this integral is called the gamma function of n. So thus the notation for this integral is gamma n is equals to integral 0 to infinity e raised to minus x raised to n minus 1 dx, and this is for all the values of n greater than 0. We know that variables are immaterial in definite integral, so you can denote this gamma function by this one of the alternate definition. Instead of x, if you replace by t, you can denote the gamma function as gamma n is equals to integral 0 to infinity e raised to minus t raised to n minus 1 dt, and this is also for all the values of n greater than 0. For example, if we have to find the value of gamma 3, so use this above definition. Here it is given in this video. Replace the value of n is equals to 3 in this integral and check. Here this integral becomes 0 to infinity e raised to x, and replace this n by 3, so becomes x raised to 3 minus 1 dx. So gamma 3 is equals to integral 0 to infinity e raised to minus x square dx. That means you can denote this gamma 3 in the integral form. Again, for example, if we have some integral, how to write this integral in the form of gamma notation? So here is the another way. If we have the integral 0 to infinity e raised to minus t raised to 5 dt, if you observe the nature of the function, which is just like the gamma function, so here compare the power of t with n minus 1. So n minus 1 is equals to 5, n is equals to 6. Therefore, the value of n is 6. So you can write this integral in the form of gamma notation as gamma 6. So in above example, this gamma 3 and gamma 6, you can easily evaluate the value of gamma 3 and gamma 6 with the help of the properties of gamma function. Here are some properties of the gamma function. These properties of gamma functions are useful to find a solution or to evaluate the real definite integral. First property is that gamma 1 is equals to 1. So to prove this property, we have the basic definition of the gamma function. Gamma n is equals to integral 0 to infinity e raised to minus x raised to n minus 1 dx. Here in LHS and RHS, put n is equals to 1. So gamma 1 is equals to integral 0 to infinity e raised to minus x raised to, after replacing n by 1, becomes 1 minus 1 dx. So x raised to 1 minus 1 becomes x raised to 0, and we know that the value of x raised to 0 is 1. So we have the integral 0 to infinity e raised to minus x dx. So integration of e raised to minus x is minus e raised to minus x, and put upper and lower limit here in this function. So you will get the value of this bracket is equals to 1. So therefore the value of gamma 1 is equals to 1. This is one of the important result which is used in the evaluation of the real definite integral. Second is again the important property. Gamma n plus 1 is equals to n gamma n. Again, to prove this second property. You can say that this is the reduction formula of gamma function also. So to prove this property, again we have to use the basic definition of the gamma function. Gamma function can be written as integral 0 to infinity e raised to minus x raised to n minus 1 dx. In this result or in this definition, replace n by n plus 1 in LHS as well as in RHS. So replace n by n plus 1. Here you will get the next step, that after replacing n by n plus 1, this is equals to integral 0 to infinity e raised to minus x raised to n plus 1 minus 1 dx. So plus 1 minus 1 becomes 0. So two functions are left here, 0 to infinity e raised to minus x raised to n dx. Now here we have to evaluate this integral within the limit 0 to x with respect to x. So apply LIT rule and use integration by parts for the evaluation of this integral. Here if you observe to apply the LIT rule, here this function is the power function. So consider this as u, and this is the exponential function. So consider this as a v and start to apply the integration by parts. So by applying the integration by parts, gamma n plus 1, by applying the integration by parts, x raised to n integral of the second function, that is v e raised to minus x dx within the limit 0 to infinity, minus integral 0 to infinity derivative of the first function u x raised to n and integral of the second function e raised to minus x dx, and integrate this whole bracket with respect to x. Next step, x raised to n, we know that integral of e raised to minus x is minus e raised to minus x. Apply the limit 0 to infinity minus integral 0 to infinity derivative of x raised to n by power function, this is n, x raised to n minus 1, and integration of e raised to minus x is minus e raised to minus x dx. When you apply the upper limit and lower limit to the first bracket, this is x becomes infinity and e raised to minus infinity is 0. So first term becomes 0. Minus minus plus, if you apply the value of x is equals to 0, second term also 0. So the value of this bracket is equals to 0. Now take this negative sign outside and this minus minus becomes plus. N is the constant right outside the integral 0 to infinity, and two functions are left inside the integral, e raised to minus x raised to n minus 1 dx. If you observe the nature of this integral, this is look like the gamma function, or the by definition of the gamma function, this is your gamma n. So in the next step, n into this integral as a gamma n, therefore gamma n plus 1 is equals to n factorial in general. So this second property is also very useful in the evaluation of definite integral. For example, we have to use this property as gamma n plus 1 is equals to n gamma n, as well as gamma n plus 1 is equals to n factorial. For that, we will see here one standard example. Here, if you want to find, or if you have to find the value of gamma 7, you can write this gamma 7 in the form gamma 6 plus 1. That means split this 7 in n plus 1 form, and using this result you can write this as 6 gamma 6. Similarly, you can write gamma 6 again using this property as gamma 5 plus 1 becomes 5 gamma 5. Similarly, write down gamma 5 as gamma 4 plus 1. Similarly, gamma 4 plus 1 can be written by using this property as 4 gamma 4, and repeat this procedure up to the last step. Gamma 4 can be written as gamma 3 plus 1. Obviously, these first terms are appear there. 6 into 5 into 4 into 3. Gamma 3 plus 1 is 3 gamma 3. 3 can be written as here 2 plus 1. So gamma 3 becomes 2 gamma 2. And finally, gamma 2 can be written as gamma 1 plus 1. And using again this result, this becomes 1 gamma 1. Since in earlier steps we know that the value of gamma 1 is equals to 1. So the value of gamma 7 you can write exactly in this form, 6 into 5 into 4 into 3 into 2 into 1. And if you observe that this is what here the 6 factorial. So we can generalize the result that gamma 7 is equals to 6 factorial in general. You can say that gamma n plus 1 is equals to n factorial if n is the positive integer. Suppose if we have the value of n in the form of fraction, again you may apply the same formula here. Gamma 5 by 2 can be written as gamma 3 by 2 plus 1. By using n gamma n, this becomes 3 by 2 gamma 3 by 2. 3 by 2 write in the form 1 by 2 plus 1 and use n gamma n property. So 3 by 2 into 1 by 2 gamma 1 by 2, and here we have to put the value of gamma 1 by 2 is equals to root pi. We will see in the next step why the value of gamma 1 by 2 is equals to root pi. So if you place the value of gamma 1 by 2 is equals to root pi, you will get the value of this gamma 5 by 2 as 3 by 4. That means 3 is in the numerator, 2 into 2 is in the denominator, and value of gamma 1 by 2 is equals to root pi. Therefore value of gamma 5 by 2 is equals to 3 by 4 into root pi. Similarly, you can find the value of gamma 5 as 4 factorial. You can write this as a 4 factorial. Value of gamma 8 you can write it as a 7 factorial. Value of gamma 7 by 2, use the above procedure. So you will get the solution. Gamma 9 by 2 you can evaluate by using the above procedure. You will get the solution of the. So this is very important result that gamma n plus 1 is equals to n gamma n in general and n factorial. Next property is gamma 0 is equals to infinity. In the previous step we have seen that gamma n plus 1 is equals to n gamma n. So this step can be written as gamma n is equals to gamma n plus 1 upon n. If we place the value of n is equals to 0 in LHS and RHS, gamma 0 is equals to gamma 0 plus 1 gamma 1 here upon 0, and we know that 1 upon 0 is infinity. So because of that, value of 0 is equals to infinity. Next property is gamma p. Gamma 1 minus p is equals to pi upon sine of p pi. This is the important result, that if we can use this result if and only if the value of p is lies between 0 and 1. This value should not be less than 0 and greater than 1. So you can use so many times in the evaluation of the integral. Property number 5. Value of gamma 1 by 2 is equals to root pi. Here in this above property, if you place the value of n, or you can say that instead of n, you can say that the p, value of p is equals to 1 by 2 in this above result. So this becomes gamma 1 by 2. 1 minus 1 by 2 is equals to pi upon sine p pi. This property is applicable because the value of p 1 by 2 is lies between 0 and 1. So gamma 1 by 2 is equals to pi. In the earlier step, gamma 1 minus 1 by 2 is 1 by 2. So gamma 1 by 2 square is equals to pi. And if you take the square root on both sides, you can write the value of gamma 1 by 2 is equals to root pi. Next important point is the transformation of gamma function. This is also useful so many times in the evaluation of real definite integral. So this result is that integral 0 to infinity e raised to minus ky y raised to n minus 1 dy is equals to gamma n upon k raised to n. To prove this result, we have to use again the basic definition of the gamma function. Gamma n is equals to integral 0 to infinity e raised to minus x raised to n minus 1 dx. In this definition, if you substitute x is equals to ky, when you substitute x is equals to ky, you have to convert everything in terms of y. So differentiate this above substitution on LHS and RHS. So x becomes dx, k is the constant, y becomes dy. When you convert everything in the form of y, need to change the limits also, and you can use this by using here this substitution. So if x is equals to ky, y is equals to x upon k. So when x is equals to 0, y becomes 0. When x is infinity, y is infinity. So here limit changes from x is equals to 0 to infinity to 0 to infinity. So use all the substitution in equation number 1. Replace x by ky and dx by k dy. So gamma n is equals to integral 0 to infinity e raised to minus ky raised to y n minus 1 and k into dy. Now separate the power n minus 1 to k as well as y. So next step is here 0 to infinity e raised to minus ky, k raised to n minus 1, y raised to n minus 1, k into dy. If you observe here, we have the two terms related to k. So let us add the powers of these two k raised to n minus 1 plus 1. So k raised to n minus 1 plus 1 becomes k raised to n. So this is the constant term you can take outside the integral 0 to infinity e raised to minus k by y raised to n minus 1 dy. And in LHS we have gamma n. So you can write that integral 0 to infinity e raised to minus ky y raised to n minus 1 dy is equals to gamma n upon k raised to n. So students, this is very important result in the evaluation of the real definite integral. To understand this above result, we'll see one example based on this. Suppose if you have the integral 0 to infinity e raised to minus 2x x raised to 4 dx. If you want to find the value of this integral, it is quite difficult for us by using the simple integration formulas. So we have to use the gamma function here. Now if you compare this result with this result, we know that this integral 0 to infinity e raised to minus ky y raised to n minus 1 dy, this is equals to gamma n upon k raised to n. So need to find the value of n as well as the value of k. So if you compare this power here, variables are immaterial in a definite integral. So instead of x, y is there. So what is the value of k? K is equals to 2 and compare n minus 1 is equals to 4. So k is 2 and n minus 1 is equals to 4. So n is equals to 4 plus 1, n is equals to 5. So if k is equals to 2, n is equals to pi, put here. So this becomes integral 0 to infinity e raised to minus 2x x raised to 4 dx, and this is equals to gamma n upon k raised to n. So value of gamma n is 5. So place this value here. Value of k is 2. Place this value here. Value of n is 5. Place this value here. Now we know the properties of the gamma function. Phi is the positive integer. So you can write in a factorial notation as a 4 factorial and 2 raised to 5. So this is the value of this integral, which you can prove with the help of this transformation. Now the last property of the gamma function, you can use this as an alternative definition of the gamma function also. Gamma n is equals to 2 into integral 0 to infinity raised to minus x square x raised to 2n minus 1 dx. Again use the basic definition of the gamma function. Gamma n is equals to integral 0 to infinity raised to minus x raised to n minus 1 dx. Here to prove this property, we have to substitute x is equals to t square here. So differentiate on both sides. Dx is equals to twice t dt, and use this substitution to change the limits. Limits for x are 0 to infinity. We have to find the new limits. So when you place x is equals to 0, you will get t equals to 0. When x is equals to infinity, t becomes infinity. Now use all this substitution in equation number 1. So equation 1 becomes gamma n is equals to 0 to infinity e raised to minus x raised to n minus 1 dx. So x is equals to t square raised to n minus 1 and dx is equals to twice t dt. Now multiply by this 2 to this n minus 1. So this is integral 0 to infinity raised to minus t square t raised to 2n minus 2 2t dt. Now we have the two terms of t. Let us add the powers of t. 2 is the constant right outside the integral 0 to infinity. So e raised to minus t square t raised to 2n minus 1 dt. We know that the variables are immaterial in definite integral, so you can write this result in the form of x also. So we can prove that gamma n is equals to 2 into integral 0 to infinity e raised to minus x square x raised to 2n minus 1 dx. This equation 1 and 2, equation number 2 as well as equation number 1. So you can use this equation number 1 and 2 both considered as the definition of the gamma function. So all these are the basic information about the gamma function, definition of the gamma function and the properties of the gamma function. Thank you.